Greetings and salutations, magical chemists. Let's talk about the glories of energy stoichiometry. But before we do, let's talk about that unit of kilojoules per mole reaction, because that's what enthalpy is commonly measured in. But the real question is, what the heck is a mole of reaction? Well, technically, 1 mole of reaction literally means this reaction happened a mole of times, 6.022 times 10 to the 23rd times. What that means for us is a stoichiometric number of moles of both reactants and products got used or created. So let's go ahead and look at the combustion of ethane, and let's go ahead and add its enthalpy value in. Combustion, of course, basically releases tons and tons of energy. It's very exothermic. So 3,120 kilojoules are released every time 1 mole of this reaction runs. And when that 1 mole of reaction has occurred, because the stoichiometric coefficient is 2, there will be 2 moles of ethane that have reacted. 7 moles of oxygen. And when you look at the products, so when this reaction ran a mole of times, well, based on the stoichiometric coefficient, there would have been 4 moles of CO2 produced and 6 moles of water. So that's what we mean by a mole of reaction. Conveniently enough, we can also use the enthalpy of a reaction. We can use that, since it's being measured in kilojoules per mole of reaction, we can use it as a conversion factor between the amount of chemicals that react and the energy that is absorbed or released. And this leads us to energy stoichiometry. It's still stoichiometry, but we're adding in one extra step. So let's go ahead and take a look at a couple of examples. So example 1 gives us the balanced reaction for iron reacting with carbon dioxide, and it gives us the enthalpy value. And we want to know, well, what's the energy change that happened if 6 moles of carbon dioxide reacted? Well, just like any other type of stoich, we're doing dimensional analysis, and we're going to start with our given. So I have 6 moles of carbon dioxide. Since I'm already in moles, I can go to my mole-to-mole ratio. Here's the weird part, and it is unique to energy stoichiometry. You're going to convert from moles of CO2 into moles of reaction. And in this mole-to-mole ratio, moles of reaction is always defined as 1 mole of reaction. And to figure out, well, how much CO2 got used up when a mole of reaction happened, you just look for the stoichiometric coefficient. Well, there are 3, that's a highlighter. There are 3 moles of CO2 that are getting used every time a mole of reaction happens. Now that we're in moles of reaction, well, we can convert from moles of reaction to energy using our enthalpy value. So I'm converting from moles of reaction directly to kilojoules. Well, in this case, remember, the moles of reaction always gets a number 1, and you're like, well, how many kilojoules got released in 1 mole of reaction? Hey, look. And actually, did you notice this actually isn't releasing energy? This is a positive delta H. So this is absorbing energy. So 24.7 kilojoules get absorbed every time this reaction runs. So mathematically, well, 6 divided by 3, right? Just 2. So you're just doubling the enthalpy. And we only started with 2 sig figs, so we get to keep 2 sig figs for a grand total of 49 kilojoules of energy absorbed, since this is a positive value. All right, let's try another one. In the second example, this time they don't give you an amount of a chemical. Instead, they talk about energy being released, and they want you to convert from that energy into the mass of hydrogen that must have reacted to produce that. Well, we can do this with energy stoich too. As always, I start with my given. In this case, 525 kilojoules. But watch out. This was released, so that must make this a negative 525 kilojoules. That's important because you'll notice we need to convert from kilojoules into a chemical, so our conversion factor is enthalpy, which is kilojoules per mole reaction. And the enthalpy for this reaction is negative, so you have to start with a negative number to cancel out the negative. If you forgot that initial negative, you would have calculated a negative amount of a chemical, and that's not a thing. So if you ever calculate a negative amount of a chemical, maybe go back and check your signs. All the rest of this is just straight up Stoich, because since we used enthalpy, we're in moles of reaction, now we need to convert from moles of reaction into moles of the chemical we actually want, in this case hydrogen. And we will of course use the stoichiometric coefficient when we're converting from moles of reaction into moles of hydrogen. In this case, it's a 1:3 ratio. Now, hopefully you noticed they asked for the mass of hydrogen, so we need to multiply by molar mass. And there you have it. Still energy stoichiometry. It's just that this time we started with energy. And we started with 3 sig figs, so we get to keep 3 sig figs in our final answer. So we have 9.80 grams of hydrogen produced if that amount of energy was released. That's it. That's energy stoichiometry. So there are some practice problems at the bottom of this page and on page 13 that you're totally going to try. But you already know how to do all of it. So for instance, we're looking at the combustion of gaseous propane. You have some questions, and then yay, stoichiometry. You should go ahead and try this entire problem. And only when you are ready to check the entire problem should you unpause the video. Yum, balancing things. I know you're excited. Okay, combustion of propane. Remember, in combustion, you always have the thing you're burning plus oxygen gas. And then the 2 chemicals produced are carbon dioxide and water. Once you know that, balancing is pretty straightforward. Notice that it asked for a thermochemical equation, so that means you needed to include the value of your enthalpy in the reaction itself. So the enthalpy was negative 2,220 kilojoules per mole reaction. Since it's negative, that means this amount of energy is produced, so it's a product. Watch out for the units. Remember, the per mole of reaction is implied when it's written within the reaction itself. All right, so the sum of all the coefficients, if you add them all up, should be 13. And this was definitely exothermic. So we wanted to know the mass of propane that must be burned to release this specific amount of heat. Well, that's just energy stoich. And since this energy was released, that is a negative starting number. So we use enthalpy to convert to moles of reaction, do our mole to mole ratio, and conveniently enough, it was 1 mole of reaction for every 1 mole of propane, and then of course, multiply by the molar mass of propane, giving us 112 grams of propane that must have been burned. All right, let's look at the next one. This, of course, just more practice. You know how to do this, so you're going to try this. And when you're ready to check your answer, unpause the video. As long as you wrote the ionic compounds correctly, balancing wasn't bad. And then this time, we had a endothermic enthalpy, which means the energy change is going to go into the reactants. And then, of course, you do energy stoich to find the energy change that occurs when 2.25 moles of sodium hydrogen carbonate decomposes. Now, crazy story here about the sig figs. You, of course, are starting with a given of 3 sig figs. You actually have to use enthalpy for sig figs as well. Normally, it's not a problem. So far, it hasn't been a limiting number of sig figs in any of our calculations. But this time it is. Only 2 sig figs, so that's all we get to keep. Okay, we got 2 more practice problems. The next one's fun. You have all the information you need to be able to do this problem, so you should totally try it. And when you're ready to check the answer, unpause the video. Okay, we have a balanced equation, totally exothermic. We're burning something, right? But then, at the bottom, it asked you to calculate the volume of carbon dioxide gas. Ooh, this is gas stoichiometry. And did you notice that we are not at STP? Shocking. Well, if you're not at STP, you have to use PV equals nRT. So the trick is we have to first do our energy stoichiometry to calculate the moles of carbon dioxide and then plug into PivNert to calculate the volume. Okay, we've done our energy stoich, we used our conversions, and now we have moles of CO2. So now we're just going to plug into PivNert. Remember to use the whole calculator answer. But other than that, this is pretty much straight up normal PivNert. Since our pressure is in atmospheres, we have to use the tiny value of R, and it only gives us 2 sig figs. So 38 liters of carbon dioxide were produced when that amount of heat energy was released in this reaction. One more question to go, and shockingly, there's no math in it. This time we're just talking about a particular chemical reaction, barium hydroxide octahydrate, and we are going to mix that in a beaker with ammonium thiocyanate, good stuff. And it turns out that has a chemical reaction, and when it does, the beaker becomes very, very cold. So you are going to use that information to answer the following 3 questions. When you have answered this question, go ahead and unpause the video and check your answer. Well, first, the surroundings must have lost heat, right? The beaker got really cold. But if the surroundings lost heat, or released heat technically, that means the system that we're studying, that chemical reaction, must have gained that energy. If the surroundings lost, the system gained. And if the system gained energy, this must be an endothermic reaction. And there you have it. We're all done. So thank you for playing with the glories of chemistry.